Good afternoon, everybody. Welcome to today's COSI seminar. I have the pleasure to introduce David Giltner today as our guest speaker. He got his PhD in physics from Colorado State University, and then he went to work in industry. So he's a scientist turned into industry researcher himself. He has extensive experience working in the industry. He worked for SDL, Ball Aerospace, and GDSU Picolite. And he happens also to be the president of the Colorado Photonics Industry Association, CPIA. Check their website, has cool information on it. And he's currently working in a project about a book on scientists turned into engineers, in the sense, I guess I'm here speaking for myself, I guess it's in the sense of working for the industry.
Yeah, right.
So, welcome.
Well, thank you. Thanks, everybody, for having me. Apologize, it seems some of the formatting and fonts on my slides were left on my computer. Something about PowerPoint I haven't figured out yet, I guess. So anyway, it might look a little bland, but I think it'll be fine. My title of my talk is The Advantages of a Science Education in Industry. And really let's see if I can get this thing to work to switch the, well, it looks like it's not working again. Just go to the keyboard here. So this talk is really about the unique qualities of a science background when applied to a career in industry. So I'll cover kind of why a scientist might want to go into industry, what some of the roles are, skills, knowledge, attributes that would be useful, and maybe some of the same things, skills, knowledge, and habits that might be important to develop. I guess I understand this is a bit of a mixed crowd, ideally some scientists and some engineers. So for the scientists, hopefully this would be useful information, kind of career management information. And to the engineers, maybe it'll give you a feel for the perspective of people with a science background that you might work with either now or in the future. My own background is to give a little detail that sort of motivates this. So I got a degree in physics, bachelor's from Truman State and a PhD from Colorado State University with my research background being in laser spectroscopy. But right after I graduated, I went into industry and spent 14 years in product development, primarily laser-based instruments at SDL in the Bay Area, diode laser products. Ball Aerospace here in town, working on laser communications for satellites, and then finally at JDSU Picolite, they made VCSELs and fiber optic transceivers for datacom. So this kind of motivates my own interest in this topic, being a scientist turned engineer. And having spent my career to date kind of working in an engineering field and really, both figuring out what some of the benefits are of having a science background, as well as the enjoyment of working in an engineering kind of environment. A fundamental difference, of course, is that engineers in general are trained to design things and scientists are not. And that's one of the challenges that a scientist can face going out in industry is, how can I survive? Maybe this is where I want to go for a number of reasons, but can I be successful designing things when I'm not really trained to design anything? Of course, my answer is absolutely, and that's what I cover in this. But the fact is, so I can speak primarily from a background of a physicist, but just in general, many scientists who might go into industry, they don't have much exposure to the commercial world at all. It's really an academic focus. Few internships and things like that might give them much exposure. They don't necessarily understand what it would take to be successful in a product development or design kind of environment, and might not really have a good idea how to sell themselves either. Now, you could argue selling yourself is kind of always a challenge for nerds or geeks like us. But by the way, does anyone really know the difference between a nerd and a geek? I know when I was in graduate school, we debated that now and then. What's the difference? But thankfully, there is a solution to this. And the best thing about it is that it's a Venn diagram. What better way to convey the subtle distinctions between a geek and a nerd and a... So of course it's, intelligence has to be in there, and obsession, that makes sense, and well, we all knew social ineptitude had to be included, so... But because of my own interest in this, and having been, at least to date, relatively successful, transferring into a product development and sort of working as an engineer, as well as the number of people that I've talked to from a science background that are also interested in this. I started a project just a couple of months ago where I'm interviewing a number of scientists turned engineers and ultimately put it in a book. I've talked to 3 people, I've interviewed 3 people formally, but I've also talked to about half a dozen others. This would really be a career management reference guide, I think, for either students or even people transitioning, after they've been out of school for a while. And I think the real benefit of it is it's not just me trying to spout what wisdom I may have, but it's really talking to it's real stories of other successful people that I think lend some of the benefit of the power of this. So, talking about career management, ultimately, I think what's important is to kind of focus on, well, what does a manager hire somebody for? What's the purpose? Because if you want to direct your career, you kind of need to understand what people are looking for. And in general, in industry anyway, really the only reason somebody hires somebody, or especially a technical person, is just to improve profits. It's all about money, either to increase revenue or decrease costs. So that's one important thing that's good to keep in mind. And what qualities might they look at? So I've borrowed these. Well, let me go through them first. I talk about skills, knowledge, and attributes as kind of the 3 fundamental things you want to think about in terms of what you have to offer a company. Skills are kind of the tools of the trade, things that you practice that you can get better at. Knowledge is facts and figures. It could be learned from a book. It could be knowledge that is picked up just from experience. But the key about those 2 things is that they're learnable. Either you can get better at them. The third thing, attributes, that's really inherent tendencies. Things fundamental about a person. What motivates them? What excites them about their job? How do they communicate with other people? How do they handle stress? How do they make decisions? These are things that tend to be pretty fixed in a person throughout their life. So you kind of have things that you can learn and that you can develop, and things that are sort of fundamental to who you are. Now, I really borrowed these from what's really a great book, First Break All the Rules, by Marcus Buckingham and Kurt Kaufman. These 2 guys are with the Gallup Institute, and this book discusses the results from a 25-year study of over 1 million employees from a wide range of industries. What they were trying to do was understand what do good managers do. So they'd look at, survey behaviors of these managers, what their employees identified with, and they'd try and correlate that to the success or non-success of the company and distill some things out of that. There's a lot in that I'm not going to go into, but I really like their way of looking at skills, knowledge, and attributes. So what I'm really doing here is just defining terminology that I'll use through the rest of the talk. In my opinion, a career plan is critical. That's certainly the way I approach it. And I think one of my favorite quotes that really says why that's important is it's from Jack Welch, who's the past CEO of General Electric. He said, "Control your own destiny or someone else will." And that's definitely important. It's definitely true. You can go through your career just kind of taking whatever opportunities may be presented to you, but the fact is, if you do it that way, it will be somebody else presenting you with an opportunity they'd like you to take, and you'll ultimately follow somebody else's idea of what your career should be, or maybe several people's. I think it's really important to have a plan, say, this is where I want to go, and this is how I'm going to achieve it, and I think it's far more successful, at least more successful at achieving what you really want, what really makes you fulfilled. So, key questions to ask yourself: where do I want to take my career? What do I want to do? What skills, knowledge, and attributes that I have can I leverage to make me successful? And of course, what things may I need to develop? Many more questions you could ask yourself, but in terms of things I'm discussing, I think these are three major questions here. So, first one, where do I want to take my career? Well, the premise of the talk is talking about a scientist that might go into industry, so let's assume that's a given here, but what I've listed here are some of the reasons given by people I've interviewed so far as why they wanted to go into industry and why they feel it was useful instead of becoming a researcher. Desire to see a tangible reward for their work. That one's pretty common. Research, of course, can be very rewarding, but for some people there's nothing like actually seeing a product, being able to hold a device that they've designed and made and are selling to other people. That can be a real reward. They want to make an immediate impact. Scientific research can take many, many years to complete sometimes, whereas product development cycles can be less than a year. You can have something that's being sold. Pretty immediate feedback. And just in general, like to create or build something. The second major theme is work and life or family balance. This may not be true if you're working for a startup. That can take an awful lot of time. But many people have cited that that's, more established companies can tend to offer a better balance of those things. Another thing is in industry you can tend to work with a lot of people. Science research, you might work on a smaller team depending on what you're doing, but in industry you'll really, in general, be working with a lot of different people. Those people may change over as projects change, and plus you have customers and suppliers that you work with as well, so it can be a large number of people. A couple of the people I interviewed are in medical industry. Boston Scientific in Minnesota and Covidian here locally, and their desire to help people was a big one. Research can certainly do that, but if you're developing medical products, those go right out into the field and are actually potentially saving lives in, a year or two, or maybe a few years for medical products. There's a pretty intense qualification procedure, but the point is it's relatively immediate feedback where you're actually helping people. From my own perspective, what do I enjoy about it? Well, I like the way it's very pragmatic. Because in industry everything's focused on the bottom line, on money, that really presents a strong drive towards efficiency that I like. It's not so common to be wasting time on something you think, there's no purpose, what are we doing this for? It's not to say that companies can't have it go down a direction that doesn't work out, but at least the intention at all times is to be as efficient as possible. I've spent some time working on government contracts, and I can tell you that is absolutely not the case. But when a company is working on a product, the goal is always, and everyone is on board with this, even if they have different perspectives on how to get there, everyone's trying to be as efficient as possible. Now, of course, that can lead to cost cutting too, and sometimes that's something you have to be okay with. There's a risk that a program can be cut, people can be cut. That's part of the game. That's the flip side. But at the very least, it attempts to be pragmatic and efficient. I also really enjoy the exposure to a lot of people, the networking opportunities. That's very fun for me. Very fast paced and dynamic, and there's always new things to learn. Things can change 6 to 12 month basis, and you can be working on something totally new with new things to learn. You can take a technology that you've developed for one market and move it into another, and all of a sudden you get to learn about a whole new application. It could be working on materials processing, and then you learn to start working on medical device or something along those lines. It can be very fun. Some of the roles, at least from the people that I've spoken to so far, are listed here. And I know I've seen a lot of things about what could a physicist do, for example, from my own background, in industry. But so I've got a similar listing here, but what I want to do as I go through the rest of the talk is talk about, when I get to skills and attributes, come back and say, where some of the people I've spoken to have actually found these things applicable for these specific jobs. So things like a system engineer. So really that's, just to give a little bit of background on each of these, in many companies there will be a role of a system engineer whose job it is to pull all the different design aspects of a product together into the top level product. There may be subsystems, assemblies that have to come together to make the final product, or it may just be a matter of leading the team of an optical engineer, an electrical engineer, and a mechanical engineer, and software engineer who each have their own parts to develop. Somebody's got to be the technical conscience for the entire system, making sure that the final device, when it's all put together, meets the final need, the specification for the full part. And it involves facilitating communication between the different engineering disciplines, and it involves kind of having a big picture view. So I'll come back to that. Technical leadership is not so different. If you're leading a development team, developing products, it still involves many disciplines that all come together to make a product. Project management typically is seen as the non-kind of technical schedule and funding part of that, but it is critical, I believe, that person have some technical understanding when they're running a schedule on a project to understand what's important and what may not be so important. Reliability engineering, it's not strictly a design function, but it's very important for product engineering, for product development, to ensure that the product meets the reliability, the lifetime, and environmental requirements. And there's a lot of science-type work that goes into that, frankly. Process development is a matter of designing how something will be put together, such that it efficiently ends up at the final part, and also so that the process is something that can be done by people who are not necessarily highly trained, may not understand how the device functions, but there's still a process for putting it together that they can understand and do repeatably. And then quality and design assurance, making sure that the final product will repeatably meet the requirements. So it's not really the same as reliability. This makes sure that it survives. This makes sure that the device that is being produced, even from when it ships from the factory, meets the requirements, and things don't vary too much and go out of spec. So I'll refer back to some of these as we go through the rest of the talk. The second major issue, what skills, knowledge, and attributes can a scientist leverage in industry? So some overall science types of qualities that I think of that are important, and from the people I've spoken to, just a scientific approach to problem solving is big. Product development, frankly, is full of problems. It starts with a customer requirement, and a company will have a technology where they say, hey, we can do that, we can put something together like that, but there's still plenty of problems along the way that come up, and that problem-solving skill can be very useful. And it really can be different than a specific design skill, and a team needs to have both of those on it. If it were easy, somebody else would be doing it, and that's absolutely true in a competitive world of industry. If there's an opportunity there, it probably means it's going to be hard and there'll be problems to solve. An internal drive to find a fundamental cause. At some level, I think this is an attribute. So certainly as a scientist, you're taught to dig kind of one level deeper and ask more questions than what might be really obvious. That's perhaps a skill that can be taught and learned. But just the personality that is prone to challenging assumptions, that doesn't just take something at face value and say, okay, that's good, and go forward with it, but stops and goes, well, why is that, and are we really sure about it, is really key in this kind of an environment. And just, again, a personality trait that something that's unexplained isn't necessarily scary, but might be interesting. Reliability engineering is an excellent example of where this is useful, and in fact, this is feedback I got from a reliability engineer that worked for me at Picolite. You're developing a product, and there's a schedule, has to be released by a certain date because the customer needs it. And along the way, you do environmental testing, you shake, shock, and vibe, and put it through damp heat and temperature cycle it up and down. And when something fails, it's not good because you have to go fix it. But if the person who's the reliability engineer actually has a little bit of enjoyment from that and says, hey, here's an interesting problem to figure out, why is it doing that? At some level, that's not so different than science research, where you have some physical phenomena and the goal is to figure out, well, why is it behaving this way? What's behind this? Can I figure out why it's doing this? Well, reliability engineering has a great element of that in it too. And while anyone can say, this is my job, okay, I'll go figure out the problem, it is a challenge. And if you've got somebody who just inherently enjoys that and says, this is a great challenge, that's who they are, that's what they enjoy, that's a real benefit. They're going to do better. And I think a lot of scientists have that kind of, that's sort of fundamentally who they are and why they got into science in the first place. Another really key aspect is kind of the whole picture view of the product or the project. It's not just a focus on a specific element or a specific part of the design, but looking at either the product itself or even the entire project as a whole picture. Why are we doing this? Who's the customer? What does it need to do? Are the requirements actually what's needed? Is also very important. I'll talk about that a little bit more in a minute. So if we talk then specifically about physics and about the physical sciences, this draws more directly from my background. So broad technical knowledge is a real plus. I like to say, well, physicists study everything. At some level, everything boils down to physics. And if you look at the design disciplines that you will typically have on a design team, in general, you're going to have probably optical, electronic, perhaps ICs, mechanical, test engineering, software design. Any of these are disciplines that will in general be on a product development team. Well, physicists at some level, most of them anyway, study most of these as well. Classes in optics and lasers and E&M. If you're an experimentalist, you probably did some level of circuit design or put together some kinds of circuits. Classical mechanics, I know as a physics grad student, I certainly spent a lot of time in the machine shop myself, making parts that I needed. Equipment design, data analysis, test automation. So while none of these give you specific design skills where you can actually do the product design like an engineer can, you still have enough of an idea that you can understand each of these disciplines. And that is helpful for a couple of reasons, I found. One is it facilitates communication, whether it's making sure that, whether it's between the different engineers on your team. If the optical engineer says, no, this device has to have 3 lenses, and the mechanical engineer says, well, I can't accommodate that, it's useful to have some understanding of both so you can work out a solution for the product. Because the fact is, if they're a really good optical engineer and a really good mechanical engineer, they may know their disciplines very well and know exactly what needs to be done, but they may not have enough of an appreciation of where the other person's coming from to really figure out how do we come to a common solution here. So that communication is important. Another area that communication is important is talking to the customer or to management, who may be less technical or at least not understand the technical details the way the engineers do. I have certainly myself had to interpret for, I'm thinking of an example of an optical engineer who was working from his ZMAX model and trying to explain why the design had to be this way in terms of the parameters coming out of the model. Well, the customer didn't understand that at all. They wanted to know physically. They had a technical background, but they didn't understand what the parameters were. And so, having some understanding, but being somewhat ignorant myself as to some of those details, it sort of helped me interpret and say, well, okay, here's intuitively what's going on, or describe from at a higher level what's working. That's one thing, one area I think that's useful. And the other I already alluded to is working with a multifunctional team and actually leading them, whether it's as a system engineer, helping you interpret excuse me, the system level requirements, flow down to the subsystems or to the individual functional designs, ensure compatibility. Somebody really has to understand all those technologies to some level. And trained as a physicist, I don't know enough about materials properties to be able to tell the mechanical engineer how he should do it, but I can at least understand enough about what he's doing and how machine tools work to be able to say, okay, yeah, that makes sense in the full system, and bring all that together. A project leader and R&D manager is another good example of that same thing. And if I again speak from experience, for example, when I was leading a team developing fiber optic transceivers, I had a team that included optical engineers, electronics, mechanical, software, an IC designer, people doing PC board layout, test engineering, and reliability engineering all on my team. And at least having enough of an overview of the different disciplines allowed me to communicate with them and make sure that the product came together, even though I could never have actually designed it myself, any of these things myself. Another common quality is critical thinking about data analysis. I'm sure this isn't just physics, but again, I can specifically address that. There can be a lot of data that is taken in physics research It's important to understand how to take the right data, especially when money is the issue and you have to be efficient. In research project, face it, grad student labor is relatively inexpensive, and you might be able to afford to take all the data that you need to fully understand the system. And that's not true in industry, where it's all cash, and every extra amount of time you spend taking data or doing an experiment eats into profits. So it's important to understand how to take the right data and what that is, how to get useful information out of whatever data there is, and sometimes how to salvage bad data. One of the guys I spoke to, Jason, who graduated from CU here, he's now up at InPhase. He made a point that one of his principles is, well, there's no such thing as bad data. Even if, I'm sure there are limits to this, but even if something isn't quite right about your setup and you realize something's tainted your data, hang on to it, because you might be able to figure out how to use that. Frankly, physics is all about dealing with things that make your data not perfect, whether it's friction, which we conveniently try to ignore but ultimately still have to deal with, or a number of other things that make whatever we're trying to model less than perfect. So it's really no different in a lab. Hands-on technical skills are very important too, because after all, product development is about building things, about making things. There's test equipment design, building validation that is important, that has to be done, prototype assembly, and even product demonstrations. So this was one of the first things I did for a tunable laser that SDL was selling. We had to put together a demonstration for an ad, and it's effectively trying to replicate a science setup. It's not quite perfect. If you know anything about saturated absorption, it's a bit clunky, but had to cram it all together to get it in the photo. And that involves putting something together. It's not a specific design skill, but it's definitely important for selling products. And that kind of gets to one of those cool benefits of working in industry, is actually seeing an ad in laser focus world that you put together, and for a product you're selling. That's kind of the, hey mom, this is what I'm working on. So the third question, what are some of the skills or knowledge or things that you might need to develop as a scientist that might not come naturally, that are very important in the industry, because there's definitely going to be plenty of that. The first really important issue that I know I had to learn and was a bit of a challenge, and a lot of people do, I don't know, perhaps even coming out of engineering, maybe this is something that I kind of have to get used to, but product development is not research. They involve technical skills, but it's not the same. And a few examples. So science research, for example, the perfect experiment is one that stays together just long enough to get the data you need. So I should comment, I've got a, supposedly this was Carl Wyman's quote, and it's secondhand, so I don't know if, but it's attributed to him anyway. The point is, this is, I think, absolutely true. If you're trying to do cutting-edge research, the best experiment is something you hangs together, you're really pushing the limit, and it hangs together just long enough to get what you want, but because you're really pushing the edge, it doesn't last any longer than that. Well, of course, that's totally different than product development, where not only must the device pass stringent qualification testing, probably has to last for many years, depending on what you're making. In telecommunications, products typically have to last at least 15 years in a wide range of harsh environments. And not only that, but warranties are given on returns. So if it breaks, there's some customer out there who's demanding a reason. They want you to figure out what's wrong and maybe even give them a refund depending on how soon it fails. So you have to do failure analysis, corrective actions. It's really a very different business. Another area is in science research. Interesting science is an adequate justification for a project. It's not always it, and obviously there's still money involved, but in general in science, if it's cool, if it would generate interesting information, that can be a justification. Whereas in product development, nothing happens if it isn't justified by money. It's got to somehow generate money. So again, reduce costs or increase revenue. Another big difference is that in science, research projects can last many years. Entire careers can sometimes be built on a single area of research or area of study, and the researchers can continually work on it, getting more detail and greater understanding, because at some level, ultimately, the purpose is to understand completely. And in product development, that's really not true. Again, it's driven by money, and so therefore projects must have a finite end. Typically, it's a product release. The customer needs it, and they need it by a certain date. So there has to be a really strongly enforced process of defining what are the minimum requirements and working to meet those and then stopping. So there's definitely a place for some of that scientific curiosity, but it's got to be tempered by knowing when good enough is and moving on. New products can often be introduced every 6 to 12 months in a lot of industries, so that's not a lot of time to get things done. Now, presumably, it's being built on a number of years of intellectual property by the company, sort of a development of technology over some time, so it gets better and better. But for a specific project or a specific product, you don't have time to work out all the details sometimes, and it can be a challenge to make yourself say, no, that's got to be good enough, and ship it out. One of the biggest problems that I've heard of from employers who have hired scientists and it didn't work out was really that. It was, they didn't know when to quit. They wanted to keep satisfying their curiosity. So there's a place where that curiosity has a real benefit, but it's got to be reined in at times to be practical. It's that pragmatic part of the some of the skills and knowledge that need to be developed. Statistics training. I thought that was interesting. At least for me in physics, I didn't have a lot of statistics training. I did take statistics class, and of course there's statistical mechanics, but not really to the level that you need in industry, dealing with large numbers of products and trying to making sure you properly deal with statistics to look at probabilities or margins of error or whatever you might be looking at. That really wasn't that much of a focus. In research, you're kind of doing one of something, and you just need data from that. It's not quite the same. Design of experiment was an interesting one, too. I actually never even heard that term until I got out of school. And I thought it was a little odd. Well, gee, science, all you do is experiments. How can I not have heard of design of experiment? And to be honest, I'm still not much of an expert on it. But ultimately, especially the engineers, I imagine, have a much better idea of this than I do. But ultimately, it's about getting data efficiently. That's more of a process of, quickly getting to, instead of taking a huge mass of data, how can you develop a matrix and kind of hit the right few sets of tests to get the dependencies, to get the information that you need as quickly and as efficiently as possible. So I'd never heard of that, and that's a good thing to focus on. Finance and business accounting is a good one. Again, it all comes back to everything is driven by money, and if you're a technical lead or a development manager, project manager, it's good to have some kind of an understanding of how money is handled with respect to a product. The way the costs are recorded, the way net present value can be calculated, which is a matter of estimating how profitable a product will be when the income that comes from it is strung over several years, and money that you get down the road isn't as valuable. A dollar that you earn down the road isn't the same value as a dollar that you earn today. Plus, then you've got expenses, some up front, some down the line for sustaining engineering. And how do you actually turn that into here's the return on our investment, which is really what people care about. That's back to that whole idea of if it doesn't generate money, it's not justifiable. So it's helpful for project lead roles, and that, in many cases, I think can be learned on the job. I certainly have. Useful habits. So on this side, I don't talk about attributes because I don't really think those can be changed. But habits are more about behavior, and behavior can always be changed. So what are some habits that are good to focus on? One is an appreciation for focusing on the application. And I think this is it can come out of that big picture view, but when you're developing a product, it's really good to keep in mind, what is this going to be used for? Why is the customer paying for this? because that helps drive that efficiency. What elements do we need to include in this, and maybe what are not so important? How can we make sure we don't spend too much time on something they don't need? I mean, ultimately, they have some requirements, some specifications they've given you, and you need to meet those, or perhaps you need to negotiate. But it's good to understand where those are, because that's kind of a big picture view of the product. It's also good to focus on the market for your products as well. Now, there will, in general, be somebody in marketing whose job it is to do that, but it's still good as the technical person to understand, is there competing technology out there? Is there something maybe we should be looking at? Because you've got the technical information, and you can sometimes do a little bit better job of that than the marketing person. Where's the market headed? Where should we be taking our products? That's all part of being better rounded in terms of product development. It's also important to remember that the data doesn't always speak for itself. I think I was a little more used to that in a science background, that you could just say, here's the data, and maybe give some interpretation, and other scientists would figure it out, and that sort of stood for itself. But in a company, you may likely have to sell it to either or both management and perhaps to a customer. You may not really understand it, may not have the time to figure it out, and if they're looking for that kind of that pragmatic view of what's going to make money or not, sometimes you have to turn it into, here's why you care. That's very important. Why is it? Why do you want to? Why is this information relevant to you? And finally, I know I've said it many times, but it bears repeating a 15th time, or however many I've said it. But everything's motivated by money. That's probably the essence of the biggest challenges that I faced going in industry and trying to be successful, is really trying to remember you can't do everything. You have to, pick and choose, and that ultimately the things that will get approved to work on are those that are believed will make money. An interesting corollary of that is I've found that it's best, in my opinion, my experience, it's best to choose a program. If you have a choice between a couple of programs, go with the one that's the best funded, not necessarily the one with the best technology. I've had that choice a couple of times, and there's always a tendency to say, hey, there's really cool technology here. But if it's not so clear that there's a really solid market for that, it's a good chance it won't last. And there's a lot of pain in that, because then you get to the cost-cutting part of, I had that choice to make back in, about 10 years ago. The group I was in was being broken into two, and one was going the way of low-power fiber amplifiers for telecommunications, where things were pretty well, a lot of things were defined about how the product had to look and how it had to be tested, and the other was high-power fiber lasers, and got to work with double-clad fiber and some really cool technologies there, and that really seemed attractive. But the fact is, the telecom market, which we all knew got really huge only a couple of years later, was here in the amplifier area, and fiber lasers really hadn't hit their stride yet. And in the end, so I chose amplifiers, and I never regretted that. It may not have been quite as interesting from a technology standpoint, but from a business standpoint, it was far more successful. And that ultimately meant that I was earlier in that group, and all the guys that in the fiber laser group who slowly joined our group as theirs was taken apart. I think it was the better choice. So that's another thing to keep in mind. So maybe the key takeaways here is that, in my opinion, science education can be great in industry. It's, scientists are sort of trained to become professors or researchers, and maybe that's kind of, if you will, the default path. But there's really, excellent opportunities for a rewarding career in industry, as I'm sure the engineers in the room obviously know, and that's why you chose that. But even, I think, not only is it just that you can survive, but there's actually a need for the types of skills and the attributes of a scientist. Those things that made you choose to go into science in the first place, there's a real use for that on a team. Because, like any good team, it requires complementary skills for the most effectiveness. And this is just one of those areas. Key things to focus on, there's probably several, but the big ones: broad technical expertise, problem solving and data analysis, and hands-on technical skills are among the most useful skills. But at the same time, you need to understand that product development is not science research. And again, work is only of value if it brings money. So wanted to comment, I mentioned I'm working on a book project, and I'm just getting started on this, but I've got a website around this. So this is actually 50 Interviews is a little company a guy named Brian Schwartz started up in Fort Collins, helping people self-publish these interviews, these books where they talk to people. And I thought it was kind of a great format to explore this whole idea. I'm kind of amazed how easy it is to engage people in this topic, whether they're engineers or scientists or even sometimes technicians. You know, it's an interesting idea, the balance between these two. And so I'll be posting various ideas and probably putting interview snippets, and I invite you to visit, and I'm curious about your comments, because the whole idea behind this project is to get input from other people and understand what are different experiences, whether it's from student perspective or people that are already out in their career. I think that's kind of the whole thing that I'm trying to encourage here. I know I would love to have had this perspective when I was in graduate school, because I got to within a few months of defending and thinking, well, this is really where I want to work, but I have no idea what I'd be doing, or how I'll go about it, or I know I've got good technical skills, but how do I really convince somebody that, hey, I can be a successful part of your team designing things when, as I said before, I'm not trained to design anything. You don't want to admit that. It's far better to go in there saying, here's the skills that I have, and here's how I know they will be applicable to what you're trying to do. Here's why you should hire me, right? That's ultimately what it's all about. So that's the URL. Anybody who's interested, I welcome you to stop by and leave your comments. There's not a lot there at the moment, but that's what it's all about, trying to build dialogue and information there. So that's everything I had. Thank you very much for coming.
We have time for questions.
This is kind of a personal question. Was that a conscious choice on your chart to go into industry, or was that sort of an opportunity that was given to you, or what made you decide to do that?
Yeah, it was a conscious choice. When I went into grad school, I just sort of assumed I would be a professor. Part of it for me, frankly, was the economy at the time, or you could call it the economy, and the fact that it looked like opportunities to stay in academia were thin. That's actually what first got me thinking about it. I saw people from bigger schools than I went to doing multiple postdocs. That was just, at that time, I think it was a little worse. So I didn't have the positive, it wasn't, there was another element where I thought, I'd really like to be able to actually make something and make things, and I think I'd enjoy that. But it wasn't as much as what I'm trying to present here, that, no, there's real opportunities, and they can be exciting if this is the way you're geared, if this is what you enjoy. So that was really what did it for me. I have a very different perspective now. Yeah?
You mentioned a few times money.
Right.
And you also sort of touched on the fact that sometimes you learn this sort of on the job, like the budgeting process or whatever. And I'm just curious from your discussions if you've had any sort of idea of whether an employer is looking at me or something like that. How much of a benefit is it for me to really familiarize myself with sort of economics of this whole process, as far as like trying to land a job?
Right out of school, probably not as important. I think, the finance, for example, that's something I didn't need early on. When at least I can speak from my experience, and I think several of the people I've talked to, that's more, depending on where you want to take your career. If you want to take it sort of, maybe not so much system engineer, but into a technical leadership role, then just kind of be aware that's something you'll want to pick up along the way. Or maybe you want to look for opportunities when you get a job and you get out into a company to actually try to learn that, so that then it'll enable you moving into a leadership role. Right out of school, I don't think that particular one, for example, is all that important. the statistics in DOE, that one I think would be more important. But it depends on where you're going. That's actually part of what, that's a great question to get feedback from people.
Yeah, I mean, so I imagine it's probably much more relevant if you're looking at, beginning or being part of a small group that's in a startup company versus a more established.
And even then, say you're in a startup company, the fact is whoever's funding that startup is going to look for people that already have that experience. So the non-technical aspects, I think, are things that, we're coming right out of school as a, relatively speaking junior person, they're not going to be looking for and probably wouldn't trust you if you said, hey, I read about it anyway. That's more for you, the next couple stages of your career, if you want to take it, where I think probably have real potential. So, yeah.
It's been my experience that many people who have technical and scientific skills have neither the desire nor the aptitude to get into a leadership position. And conversely, a lot of corporations have the attitude that a manager is a manager is a manager, and that anyone with an MBA can manage any group that needs to be managed. The MBA doesn't need to know about the technical details. I wonder if you care to comment on that dichotomy.
Yeah, boy, that's a good question. So it's sort of two elements to that question, right? One is the interests of the employee, and the other is more the structure, the culture of the company. In terms of the interest of the employee, absolutely. And some people, they don't want to get into any leadership role, and that's certainly fine. Things like reliability engineering, even a system engineer, those don't have to be leadership roles. To some extent, system engineer kind of is because you're trying to bring everything together, but it's not a management role. It may be a leadership role, it's not a management role. Reliability engineering can stay pretty technical. Process engineering and quality assurance, those can stay pretty technical. As well as, there are roles for, some companies still have somewhat of a research arm. Now, it's not like science research. Sometimes those work well for people who really still like more of a research, they want to work in the lab. That can be a good place for them and not have to go into management or leadership. Now, in terms of the style of the company, absolutely, there are companies where managers are not a figurehead, but they're not technical. It's simply a matter of wrangling the team, as opposed to a technical leadership role, and that really depends on the company. That's something I actually tend to stay away from. I've had some of that experience, and I don't like that for a number of reasons. Project managers are the same way. There are companies that will put a project manager into a project who they're just a project manager and they don't understand the technology. I don't think that works well in either case, managers or project managers, because ultimately you have to make a lot of decisions along the way, and if you don't understand the essence of why things are happening, I don't think you can properly make those calls. I don't think you appreciate what the priorities are. I think it can lead to driving on actions and goals that maybe aren't so critical, and they just don't understand it because they don't have a good feeling. So, but there are plenty of companies where the managers are still relatively technical, and it's not at all a, hey, I'm a manager now and I sit in a desk and I tell people what to do. It's much more of an active, just kind of a lead role, and how can we as a team accomplish this great task? That's the kind of technical leadership I would expect some scientists anyway would be much more interested in. They stay in the technical details, they stay in the problem solving, it's much more engaged, and it's not this MBA kind of manager role that does exist. Does that answer your question?
Yeah, basically. And for what it's worth, I used to write software for a living, and I worked under half a dozen different managers during the 20-year career. And my experience has been that the best managers were the ones who knew a little about software. When I had the misfortune to work under a manager who knew nothing about software, it was usually disastrous. So
I would agree with you. That's been my experience too, that I think the manager needs to have some technical background, and I think it makes it much better. Yeah.
Could you expand a little bit on what you meant by statistics? Because as engineers and scientists, I think like statistical analysis of like a data set is almost a given skill. But you had mentioned it kind of also in the capacity of like a test audience and product development.
So yeah, so a couple comments. My first comment would be my understanding from my experience, engineers are far better trained in it, and they would get a lot of that training in statistics. I mean, I didn't go through engineering, so I can't say that's always the case. As a scientist, I really did not get very much at all, so that would be one distinction. I think engineers might be much better prepared in that way than scientists, perhaps. Certainly, I've spoken to a number of scientists who said, I hardly got any of that. So I think that may be a clarification to that first point. It's really not a given in some cases.
Specifically, you might mean like legal statistics and stuff
Yeah.
like that, right? And I'm kind of curious, I don't know if that's even offered here. Does anybody else know if they offer classes in legal statistics and stuff related to engineering a product to fail a month after the warranty expired or anything like that?
There's stats classes and you have problem sets similar and stuff like that. But, it's not like a whole course.
Yeah.
dedicated to engineering statistics.
So you're saying even in engineering it feels like maybe you don't?
I haven't. I don't know if I'm on I haven't gotten any training like that. I don't know if
Yeah.
I'm on track to. I mean, some of that stuff goes pretty deep. Like even doing like a couple of problems on that. Like,
Yeah. Well, that's an excellent example. Weibull statistics is a great one because that's a failure analysis.
yeah.
It's statistics for failure analysis. My experience with it was in fiber strength, optical fiber. It's glass, right? And if you pull in the fiber and measure how long it takes to snap, Weibull statistics will give you an idea of the strength of that fiber, and it's a function of the defects in the fiber and the tension. I had never heard of it before, actually, and yet it's very important. And it's used for, I think, many failure mode, much of failure mode analysis. Now, you don't have to be trained in it. The other thing I'd like to believe is I was sort of trained learned how to learn. And in fact, I prefer it. There was some point where I was done taking classes and thought, you know what, I'd much rather give me something I need to figure out, and I'll go figure out how to learn it rather than sit in a lecture. So I think that's a success story. But still, it's nice if you've seen something, or maybe it's just a matter of telling people whether you get it in school or whether you go look at it yourself. Be aware that this is pretty important. It's a key. Yeah.
You kind of present this as when you're making career choices to choose. I'd rather either go into academia or industry.
Mm-hmm.
In your interviews with Dr. People, did you meet other people who started in one place and went the other, and one switched more common than the other? Is that even a reasonable thing to plan on doing?
Well, that's a really good question. No, let's see here. No one that I've spoken to yet has done that. I've heard of people who maybe went through a research career and then somehow had a hand in starting a company. There's a number of CU professors who have done that. I'm not aware of too many people that have truly made the switch full time. They just keep one day a week or something. They do that, and it's really a matter of using their technology. I had a couple of professors at CSU in grad school who had gone the other way, started a career in industry, but they were really at big research labs where the work they were doing wasn't product development. It was really much more like their research in academia. Because frankly, I think in most cases to get a job in school at a university, you have to be pretty well established in research. That's the purpose of several postdocs. So you've shown, yes, I can get research dollars. Yes, I have one or more research areas that are well developed and I can support. And coming from industry, to product development industry, because a lot of these big research labs really they've been cut way back. They don't really exist anymore. I think that's a very hard thing to do. So I don't want to ramble too much. I think the real answer is, it's not to say it can't be done, but I think there are some extra challenges there, and I've not yet talked to anybody that really successfully jumped.
So
Right? Yeah.
You are training scientists and engineers about industry.
Right.
So what about the companies? Are they aware of what scientists and engineers or scientists specifically can provide them?
That's a good question, and that's something that's part of my interest in this whole project, and I don't know that they necessarily are. I've been thinking about that and paying attention to job openings that I read. It's not uncommon for it to say in the requirements, degree in some engineering discipline or physics. They'll throw physics in. So at that level, perhaps they are, but I'm not sure it's really an awareness to the point of saying, yes, there's a special set of skills here that might actually be useful for this role. I mean, it's not too often, let me rephrase this, it's not too often to see a job description that specifically asks for a scientist or a physicist, because perhaps what they want are some of these skills that may be more prevalent in science than in engineering. I haven't seen that yet. Yeah.
Kind of related to that, can you comment on your own feeling, maybe those of the people that you interviewed, for how relevant the credential is, what the credential is in, specifically what the degree, how advanced the degree is, as you advance into a professional career, like 5 years in, 10 years in, 20 years in?
Yeah. So that's one of the key parameters, right? How far away you are. Yeah. Right out of school, the degree is going to mean an awful lot. Yeah. Further down the road, they look more towards what are your successes, and education becomes far less of an issue. Could I give a time constant on that? It's a little hard to say. 10 years out probably doesn't matter so much. Not that they wouldn't look at it, but I don't find. So I'm 14 years out from defending, and it really never comes up. So yeah, somewhere between 5 and 10 years, it probably starts to evaporate. Part of it depends on how much you change jobs and how well known the place you worked at is and how well you're able to describe, independent of my training, here are specific things that I have done. That's sort of it's a related but different piece of career management advice. Describe projects. Think of your career in terms of projects, because those are easy for people to understand. That starts to get past that whole issue. If you can say, I did this project, here was my role, and here's what I did, kind of doesn't matter what your training is necessarily in. Right. Now, all that said, there is another parameter in here, and that again is the company. And some companies look more to that than others do. Companies in, so at Ball Aerospace, I know they looked more at the specific training, because they work in a matrix environment where you don't report into a project, you go into a pool of engineers, right? So there's a group for mechanical engineers, and there's a group for electrical engineers, and there's a group for software engineers. And it's a different approach. They're wrangling all these engineers, and they just need to fill their team with a bunch of, it's kind of a, you're almost a tradesman in a sense, right?
Sorting by discipline.
Yeah, they really are, and they don't have a project. It's not a matter of, hey, we have this problem, can you as an individual person solve this problem? It's, we don't really know what you're going to have yet. You're going to go into this pool of engineers, and we need to know what you're trained in. And that's more about your degree. So they focused a lot more on the degree. Smaller companies I've been associated with, SDL was a great example. It was 500 people when I joined. So I came right out of school, but just in general, their approach was much less about the degree than what can you done, what have you done, what can you do. And even better, once you get in the door, a smaller company like that can be better about, giving you new responsibilities based on what you can do and really paying attention to that. Where I know in Ball Aerospace, it was still more about, do you have the credentials for this job? Not, do I as your manager realize you have what it takes regardless of what's on your resume or what credentials are?
I've heard multiple times, and I guess it's dependent upon the company, that even getting a full doctorate at times can be a disadvantage to getting some positions, especially when you're doing product development and things like that, because they're not necessarily looking for that heavy research background. Have you found that, or seen that in any of the people you've talked to that were getting too much knowledge, or like to go into industry, or like companies see that as a disadvantage, as more of an advantage at times?
It's a really good question. Let's see. So I haven't focused real strongly on that, and I can't say I've got great data exactly on that, because it's maybe hard to know from an individual standpoint. You have to have been told you're overqualified, or else you don't really have a good feel. There are certainly roles, many roles within a company where they're not looking for, full PhD level skills. That is true. Part of the efficiency, a simple way to think of it, is part of getting that efficiency is defining roles so that they require as few skills as possible. That's kind of what manufacturing is about. You want to be able to, the people assembling the thing, you don't want to pay PhDs, you don't even want to pay bachelors, you want to, quite frankly, find the most inexpensive person you can, and then get one PhD to train a process, to develop a process that this person who is very unskilled can do repeatably. That's the way you save money. So they do want to create as many lower level roles as possible. But I want to say what I'm thinking here. So yeah, I mean, it will certainly price you out of some positions. But at the same time, I'm not sure those are positions that a PhD might want to have in the first place. So the kind of personality that would go after a doctorate degree probably doesn't really want those anyway. They're probably looking for more. I'm not sure I'm explaining this very well. I mean, I don't think it pushes you out of positions that you would want in any way. I think when you have the motivation to complete a doctorate graduate degree, you're probably looking for a higher level position, and that's fine. And I haven't seen any problems there. There seems to be a pretty good fit between, the level of ambition and the kinds of opportunities there are. There are fewer of those, but.
Thanks, Dave.